Alright, hey guys, what's going on? So today we are going to be continuing on perturbing the Riemann and Ricci scalars. And in this video we are actually going to focus primarily on this guy right here, because we worked on this guy last time. Okay, so make sure to hit that like and subscribe button. You can make sure to also go into my Patreon page if you want to support the channel, and get notes if you want notes for these as well. So with that being said, let's dive straight into the topic. Right, so today we're focusing on this term of the Riemann curvature tensor. And here it is, right? So this is straight up. We just plug in what we have for our connections, and we're just really gonna play with this now because this is the Ricci tensor, and so the Ricci tensor is we want to identify the mu's with or we want to identify rho, right? So we're going to have, right, so we have here, I'll just write this out. So R mu rho nu rho. Okay, so here where these rows are is where these is why we have rows right here, right? So we're really just, I sort of skipped a few steps here, but the idea here is we have rho, and rho. If you take a look at what the Riemann curvature tensor looks like, you'll understand why we have a lot of rows here, right? Because we're identifying that this here is the Ricci tensor, right? It's a contraction of the Riemann curvature tensor. So when we do that contraction, this is what we get, okay? Within, and then there's going to be higher order perturbations as well. We're going to ignore those. And so let's go ahead and play with this now, because what we're going to get here is this is really what it is, right? We could stop here, but the idea here is that we want to calculate this here, this object here. The reason we want to calculate it because later we're going to calculate stuff like this, g mu nu mu nu, right? Because this is going to be an action for a Lagrangian, a quantum gravity Lagrangian, right? So quantum gravity Lagrangian. So we want to calculate this here. We're going to approximate it using this because, again, if we do mu nu plus h mu nu, then this guy is going to give us these higher order terms that we don't necessarily need or want. Okay? Because they're going to play negligible role in this calculation, or in the physics of things. Alright, so we can raise and lower indices, right? So this is our equation. When we raise and lower indices, we'll see this here was just the trace. We can raise sigma, or no, we're not raising sigma, right? We are, what's going on here is we can lower rho, right? Because when we lower rho, we're not really, this is just, we're not really changing the sign or anything like that. This is just, again, a dummy variable. So that's going to be this guy right here. This guy right here doesn't change. And then this here, right? So what we are doing here is we raise, here we have mu and nu. Here we have mu and nu. So that's this term right here. These two terms here. Well, we raise, let's see, we can, these two guys are essentially the same thing, right? Because we have sigma, mu, nu, mu. They're just dummy variables again, because we're summing over the dummy variables. These are all just summed over. So these are the same thing, so we have two of them. All right. And then we have this term here, which is right here, right, because we're raising nu. This term here, which is this right here. This term here, which is this right here, right, again, because we're doing this over dummy variables, right, so, and we're also raising and lowering things, right, so we raise nu to get mu with, again, the Minkowski metric. And then here we have, right here, this guy we have here, and then this guy we have right here, right? So we haven't changed a lot of these guys because, again, this is just really when we multiply the Minkowski metric, we're not actually really doing anything. And raising and lowering indices on these perturbations also, it doesn't really do anything because we are again, a lot of this is just dummy variables. And so we can combine all of these together and we get all of this mess of a thing, right? So we multiply this with this, we get this here. Same thing, right? So this multiplied with this, we get this one, and then multiplied with this multiplied with this, we get this. And so we can play this game, right? I'm not gonna like go through all of this, right? But what we'll find is that in this term here, there's actually going to be a lot of canceling, right? Because we can swap dummy indices, right? So here we can swap mu and sigma, right? And when we do that, we get mu and sigma, right? So we swap those two guys. We have them here. These two guys become the same thing. Same thing here. We could swap mu and sigma here. Again, just dummy variables. Swap mu and sigma here. Again, dummy variables. So a lot of this stuff is going to cancel. And then these guys are going to cancel also when we take a look at those dummy variables. And then here and here, these two guys are actually going to add up, right? Because they're, well, not add, right? But one's 1/2, the other one's 1/4. And these guys are the same, right? Because we have rho, sigma, rho, right? Nu, sigma, nu, okay? And then sigma h, sigma h. So again, dummy variables. We can add these guys up, and that gives us a positive 1/2 term in front of there. There's that positive 1/2 term. And then we carry this, so this guy is right here. This guy is the next term. Right, let's see if a lot of this, we're also changing dummy variables also, right? So we have sigma, mu, rho, right? So that's, let's see here, sigma, 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 right? So here's that sigma, sigma. And then rho, sigma, rho. Let's see, rho, right, so we have rho, mu. Let's see what happened there. So we have a mu here, and that is going to be, so we have mu, rho, sigma, rho. So we're changing the sigma and the mu, okay? That's what it looks like, what's going on here. And then, yeah, so this term is this term right here. And then this term here, rho, sigma, rho, rho, mu, sigma, right? So that's, this term looks like this term right here. So what ended up happening with this term right here, which looks like this term, it looks like it ended up getting added to this term right here because we have d sigma h and a d sigma h, and then d nu sigma, nu rho sigma. Okay, so again, dummy variables. So these two guys get combined, and they give us, let's see, this term right here, right? Because we have, let's see here. So this was our, so this term here is right here. Let's see, right? So this term here is actually this term right here. All right. And then do a different color. Oh wait, no, sorry. Right, so yes. Right, so this term here is this term right here. And then this term here is right here. And let's see, these two guys are right here. So that's what's going on, okay? And then these two guys, so that guy is right here, and then this guy is right here. And we need to put a red right there. So, okay, so now we can follow, right? So this is the red term, the green terms are right here, and this green term is this one. They'll get added up to give us this 1/2, and then this green term here, and this black term right here. And so, that was a lot, but we get this right here. So this is R mu G mu nu, okay? And I don't want to overbear you guys with too much here. Again, the idea is okay, we have R mu nu now, okay? Because what we did last time was we found 1 R mu nu and 2, now we have 2 R mu nu, okay? When we add these two guys up, we get R mu nu, all right? And so now what we want to do is we want to find mu nu R mu nu, right? Because this is important. This is going to show up in our Lagrangian, for quantum gravity. Okay, our Lagrangian for quantum gravity, again, is going to look like this. Right, we essentially found this part, right? And we're going to calculate this explicitly in the next video. This part we're going to add to that as well. We need to understand, though, the determinant of the metric in terms of this H. Right? So if you recall, this all sort of stems back to the idea of we are linearizing G, the metric, as flat space plus some perturbation in flat space. So we want to find now the G, this guy, in terms of this guy. Because we've found now R alpha beta mu nu, R beta nu, and R, all in terms of that, okay? It's a lot, right? it's a lot, but we're going to be happy with ourselves when we get all the equations down so that we can really just plug things in and see and find out that the quantum gravity Lagrangian is going to give birth to gravitons. What that means is that when we plug all of this in to here, we'll find out that the quantum, actually I'll do it like this, that the quantum gravity Lagrangian, is going to have some spin. It's going to look like a spin 2 Lagrangian. A spin 2 Lagrangian, and when we get that, we're going to propose gravitons. Alright. So we're almost there. We're almost to the point of building this quantum gravity Lagrangian, and so hang tight. Make sure to stay in tune with this playlist because we're going to get there, and then once we get to gravitons, we're going to talk a little bit about them. We're going to apply some quantum physics to them, and then after that, we're going to start talking about string theory. And then after string theory, my aim is to get into loop quantum gravity. And then after loop quantum gravity, the aim is to get into the ADM formalism and the ADS-CFT correspondence. So with that being said, make sure to hit that like and subscribe button. And make sure to go into my Patreon page if you want to support the channel and get notes. So I'll see you guys in the next one. Bye.